Yeah, thank you. Is it okay? Is it microphone works? Yeah. Now good, yeah. So thank you very much for organizing the meeting and opportunity to give a talk here. It's very convenient for me because the Warsaw University campus is across the street from my house. So it's walking distance, and also it's quite close to the place where I work. I work in the Center for Theoretical Physics, Polish Academy of Sciences, which is located in Służewiec district, 5 kilometers away from here. And I am leading the relativistic astrophysics group there. And I will tell you today about several projects which me and my students and postdocs are doing. So please be patient because it will be a little bit messy talk, and I will not go into much details in this presentation, but I just want to give you information what is going on here in Poland, in Warsaw, in the topic of collapsars, collapsing massive stars. Specifically, we are focused on long gamma ray bursts that are originating from collapsing massive stars. And me personally, I started my research career with hydrodynamics of the accretion disks around black holes. Actually, it was not connected so much in my early times with explosive phenomena. But I try to apply my methodology also to these events where the accreting black hole is a source of power to the relativistic jet. And this jet, in the case of long gamma ray bursts, must break out through the stellar envelope and find its way towards the observer emitting gamma rays. The jets are common in the universe, as you may know. They are also phenomena at larger scales powered by supermassive black holes. And all of these jets need a central engine. And in our paradigm, this central engine is a magnetized accretion flow. And the accretion disk's magnetosphere is anchored to the black hole's magnetosphere. And these magnetic fields mediate energy extraction from the rotating black hole. So this is called the Blandford and Znajek mechanism, which is a very powerful mechanism of extracting rotational energy of the black holes. This black hole is twisting open field lines and helps also the jet collimation, sort of kind of paradigm is established now. And numerical methods are used to model these phenomena. Back in time, people figure out some distinct mode of accretion that is called the magnetically arrested mode. Here, the poloidal magnetic field is accumulating close to the black hole horizon and prevents from escape as a result of the inward pressure. And the phenomena were studied first in the axisymmetric case, in the Newtonian or pseudo-Newtonian regime. And people find out that the gas must accrete as magnetically confined blobs. But of course, in reality, the situation is non-axisymmetric, and the gas must form some streams which have to somehow accrete to the black hole, and through magnetic reconnections also it is possible. Presumably, this results in some time variability that is observed in the real sources. So here you see a variety of the gamma ray burst signals in high energies, and their variability are described quantitatively with power density spectra. These show some characteristic slopes in the prompt phase of the gamma ray emission, and it is nicely explained by the magnetically arrested accretion. We need numerical simulations, of course, apart from some semi-analytical models. So we need to do also numerically the things, and in general relativity. So now going from the old works by Igor Gumienchev and Abramowicz, now we have better tools to describe the magnetized accretion onto the black hole in general relativity. And the codes we are using were established many years ago, but in fact, people started from modeling the black hole accretion flows In case of ideal gas approximations, don't think too much about microphysics. Now, in case of gamma ray bursts, we really need to deal with the microphysics in a detail. So we need to develop our tools to cover not only the magnetic magnetic flux evolution, but also evolution of the chemical composition and thermodynamics coupled with this. So I'm working on my code for many years with people in my group, especially thanks to Kostas Sapontzis for helping parallelization of the code, which evolved from the 2D serial code written in the group of Illinois many years ago. But we develop our own versions. One of them is publicly available, but it is using a simplified two-parameter equation of state. Now we are working with a better one, three-parameter equation of state, and also we trace the microphysics in the accretion flow and outflows to follow the composition changes. And we also worked out the parametric evolution model, which I would like to show in the end some results of the recent modeling. So here the plot shows how the structure of the inner parts of the accretion flow look like. You see in the left-hand side figure the distribution of density in the central engine. This is the poloidal cross-section. On the next plot, you see the total energy content in the jet. So it is composed from the matter and electromagnetic parts. So the jet here is mostly Poynting dominated, highly magnetized. This sigma distribution shows you the magnetization of the gas and the local Lorentz factor on the right side. And the Blunt-Fortensnake process efficiently extracts the rotational energy of the black hole. Here you see the ratio of the rotational frequency of the magnetic field with respect to the angular velocity of the black hole that confirms the efficiency of this mechanism. The jet is varying. This we may also probe with the time variability of the jet energetics at the specifically chosen points, locations in the jet body. And this project with my former PhD students, Shika Palit, who is now a postdoc in Taiwan, and Bestin James, who's starting a job in Czech Republic in Brno, stellar evolution group. They modeled the power spectrum of the model light curves and compared them with the power spectral densities of observed GRBs. And they also figure out there is some correlation between the power law slope and the black hole spin, which seems to depend on the jet Lorentz factor, the scatter in this correlation here in the plot. All right, but as I said, we want to study not only the jets and their variability, but also the properties of jets in connection with the accretion flow properties, which are actually very different from any other types of accreting black hole jet engines. Here in gamma ray bursts, we have the neutronization, and heavy elements are being synthesized in the outflows from the disk, not necessarily in the jets, but in the surface layers of the accretion flow and winds. So here we have the possibility to study nucleosynthesis pattern computed from the outflows. We are doing that via the post-processing of the accretion model results, and we study nuclear reaction network results. We need to define where is the first and second peak of the R process, and if we get enough elements to compare our results with observed phenomena like the kilonovae. We also want to know if the GRB jet mechanism is relevant here with respect to the collimation. And we found out in one of the recent works that the this wind contributes to the collimation. Here, I guess Gerardo may tell you about the results, how the jets are being collimated by the accretion disk winds. Okay, maybe a few words about our current projects. Disk winds produced in post-merger systems can contribute to powering the kilonova, but also we study different possibilities. So we want to study collapsers, and we want to actually, I will go now to the last part of the talk. I skipped that a little bit because of the lack of time. Now the application of our code to collapsing stars. So this project was actually motivated some years ago when we studied maximum stellar rotation that is needed to form a black hole, but without accompanying luminous transients. So we wanted to explain some disappearing stars in that paper with Ariadna Murguia. But the version of the code used at that time was quite simplistic. There were no magnetic fields, no jets, only the centrifugally supported disk existed. And we studied how much of the energetic feedback is possible if stellar rotation is high enough. And then we evolved our code from this simple collapse scenario to, first of all, cover the space-time metric evolution due to the changing mass and spin of the newly formed black hole. And recently, we added perturbative terms due to the self-gravity of collapsing core. This was initiated by my former postdoc Petra Sukowa, and we published a number of works about this. You may find details of the implementation of self-gravity in that works. In recent studies, we found that self-gravity additionally affects the black hole spin and mass evolution. Here you see in the plot the evolution of the black hole spin that is very dramatic at the early phase of the collapse. Then the black hole spin can decrease to about a small value that is probably not enough to power relativistic jets via the Blandford-Tenz-Nayek process that scales quadratically with the black hole spin value. We also found some density and pressure inhomogeneities and expanding accretion shocks. And we wanted to see what is the effect of the magnetic field. For the first time, we did this in a two-dimensional setup. So we adopted a weak poloidal magnetic field. We found some magnetically arrested state of accretion that is developing in this setup. So here you see the distribution of the magnetically arrestedness parameter that is basically the ratio between the radial magnetic flux on the black hole surface area divided by the mass flux. So if this value is roughly above 10 or 20, you call it MAD state. But in this two-dimensional simulation, we found only the repulsive effect of the black hole's magnetosphere, while the jets were not able to break out from the envelope. And we thought that we need a 3D simulation to really verify that. Or we need a larger scale simulation also. That is the collapser simulation challenges that are studied by Gerardo Urrutia. I hope he will tell you more in the next talk about his simulations, while we did some preliminary studies with our small scale code. And you can see the details in the posters. Specifically, I want to address you the poster by Piotr Płonka about self-gravitating collapser and jet launching. He managed to successfully launch a jet from self-gravitating collapsing stars. We plan follow-up projects with gravitational waves from accretion disks, from jets, and we welcome everybody to collaborate if you want or discuss the results together. the follow-up projects on disappearing stars and ejecta role in the jet collimation and determining the opening angle of jets. Potentially, we will have a new opening of postdoctoral position in my group next year. So please stay tuned. Our group is small and friendly. So I hope you can enjoy living in Warsaw here and yeah, all these nice places that you can visit. Also, we have access to large-scale computing facilities via the PL grid infrastructure in Poland and also in European facilities. We use at Lumi supercomputer. And finally, I want to thank the Faculty of Physics here in this department because it was a privilege for me to give lectures and have very talented students to supervise, because this is not the case in the Academy of Science where I work. Thank you.
Questions? Anyone? Chris? No, let's go. Start with you, Thomas.
I think this is a quick question. You were saying what your disk mass ejecta was, and it seemed like it had a range from 10 to the minus 4 to 10 to the minus 2. Is that because the fraction of the ejecta, fraction of the disk mass is changing, or is it because the disk mass is changing?
You mean here?
Yes.
Yeah. That's a very good question, because it actually depends on how you estimate the disk wind mass. I should acknowledge my postdoc Fatima. She did very detailed studies with various methods. So she used the Bernoulli criteria, the geodesic criteria, and finally from tracers distribution also. She had the different results because of the tracer setup in the initial condition, how many of them and where you launch. So this is the maximum value she got, 10 to minus 2 solar mass from some fiducial simulation, let's say.
So this means that the uncertainty can be still quite big.
Yeah, numerically it can be quite big. Yeah.
Very interesting work, very much information in a short time, therefore a lot of questions. Let me focus on two aspects. First, you had shown some slides about disk or post-merger ejecta with nucleosynthesis. What was the neutrino treatment in those models?
Yeah.
What did you do for the neutrinos?
Yeah, maybe here. Well, for neutrinos, here we have leakage scheme. This is,
okay, and
these on the radial rays, optical depth is computed.
Okay, a leakage treatment, yeah. And for the other, I don't know exactly whether these were two different projects or a project which was done in steps. The collapsar disks and the jet formation scenarios. Did you have neutrinos in there? And
no.
Okay.
No, here no neutrinos. It's
my question would have been on the nucleosynthesis implications, but without neutrinos, I think you.
Yeah, we are on the way to do this. Yeah, hopefully next year with more computational resources. But yeah.
Yeah, sure. Thanks.
Yeah.
Olivia.
Thank you so much for the presentation. I have a question about the collapsar models. Why do some collapsars have one columnated jet while others have two that are coming out of the opposite sides of the poles? Is there a specific reason for that?
In our case, there is no reason for that. The structure is either axisymmetric at the beginning, or there can be breakup of the axial symmetry, but then you always have two jets that can somehow presses around the axis of symmetry if they get tilted, but there is no reason why there would be no counterjet at all. Yeah, so in my case, there is no reason for that.
Thank
you. Have you seen numerical simulations with only one-sided jets?
In one talk a couple of days ago, there was a simulation, and I was also curious.
Was that an MHD calculation?
The authors of this simulation, why was,
I think there was a Kuroda model. One of the 2020 paper that you showed. Yeah, if it was full GRMHD and it showed one single lobe.
Some of mine only have a jet in one direction as well.
Yes, whether powerful magneto hydrodynamic simulation or MHD effects were just on top of the adrenal heating, in which case you can indeed get one-sided explosions. That is the question.
And there is no answer. It could be.
What's the physics reason why that happens?
Okay, we can discuss that a bit later. And let's thank Agnieszka again.